3.3 is kind of the point that we've all been waiting for. This is the first one that you feel like, oh, I feel like I know what I'm doing. So just kind of, this is very much an algebra type lesson, just at a calculus level. So we're going to look at each of the different rules to find derivatives of functions. The first one is finding the derivative of a constant. So let's just think about an equation that's a constant. So y equals 2. Then if I graph this equation, it's just a horizontal line. Now, this says the derivative of a constant equals 0. Why is that? If we look, the slope all the way along a horizontal line, the slope equals 0. And if you recall, the derivative tells us the slope of the tangent line. Well, when you have a horizontal line, it's just the slope of the tangent all the way across is 0. So that's why the derivative of all constants is 0. Okay, so let's think about if the equation of a constant is just a flat horizontal line. What does the graph of this line look like? We start at -1 up 2 over 1. A linear function also has a constant slope, but it is not 0. In this case, my slope is 2. And because the slope is constant throughout the line, then your derivative, in this case, the derivative of y with respect to x is 2. So if it has a slope, whether it's a 0 slope or a numerical slope, in the case of a line, your derivative is just that constant value. All right, so let me just show you some, for instance, if my function is x squared, the derivative is 2x. If my function is x to the third, my derivative is 3x squared. If my function is x to the fourth, my derivative function is 4x to the third. All right, so where did this 2 come from? The exponent. Where did this 3 come from? The exponent. Where did this 4 come from? The exponent. So each time what's happening is we're dropping the exponent to the coefficient, and our exponent, we're subtracting 1 from the original exponent. My derivative is always 1 degree lower. So our power rule for derivatives is lower the exponent to the coefficient and subtract 1 from the exponent. Now, if we have a constant times a function, we can just pull the constant out in front and multiply it times the derivative of the function. So where this comes into play is if my function has a coefficient, my derivative is 3 times the derivative of the function. So notice what we do. We take the exponent times the coefficient out front and subtract 1 from the exponent every time. Now, each of the cases I've shown you so far is just one term. If we have a polynomial with multiple terms, we just add or subtract the derivatives all the way across the polynomial. For example, Notice P is in terms of T. So we say the derivative of P, we just literally go dP in terms with respect to T. The bottom variable is always what's on the other side. All right, what's the derivative of T to the third? Drop the 3 to the front, subtract 1 from the exponent. Plus, this always just matches, bring that down. The 2 gets multiplied times the coefficient, 12, t to the subtract 1 first. Minus, anytime you have just a single variable, the coefficient is the derivative. So notice, everything's always 1 degree lower than the original function. T to the third turns to t squared. T squared turns to t to the first. T to the first just turns to a constant, and the constant goes away because the derivative of a constant is 0. Okay. Horizontal tangents. As soon as you see the word tangent, you're going to take the derivative of the equation. So the first thing I'm going to do is take the derivative. The derivative of x to the fourth, 4x to the third, minus the derivative of 2x squared. I'm going to take the exponent of 2 times the 2 out front, subtract 1 from the exponent, and the derivative of a constant is 0. Now, horizontal tangents means my slope is 0. And in this case, the derivative is my slope. So I want to know, when does the derivative equal 0? So how do I solve an equation that equals 0? Your first choice is always factoring. So notice there's a GCF for x. So I'm going to factor out 4x from each term. So we technically just divide each term by 4x. So here my 4 goes away. I take one of my x's out. I'm left with x squared. 4x divided by 4x is 1. I can then factor x squared minus 1 into x plus 1, x minus 1. I now have 3 factors. What makes each factor equal 0? When x equals 0, or when x equals -1, or when x is +1. So let's think about the graph of x to the fourth. Typically gives us a W shape. This says there are 3 spots that have a horizontal tangent. So where my slope is a horizontal line. And that makes sense. This is all using your calculator. So if you want to plug this equation into your calculator on a standard viewing window, if you plug in your equation and you do not see this graph, go to Zoom, and I believe number 6 is Zoom Standard. That will automatically change your window to -10 to 10 for both the X and the Y. That's a helpful feature. Okay, once you have it graphed, we're looking for these horizontal tangents, but we're going to have the calculator help us. Now remember, on the calculator, you need to have 4 decimal places correct. There's no way you can estimate that. You have to have the calculator do it for you. And so what we do, the horizontal tangents on the graph end up being your maximums, your high points, and your low points. So what you're going to do, you're going to tell the calculator you want it to calculate something for you. So you're going to push second, the light blue button, second calculate or second trace, and we're going to look for this is a min. So tell the calculator you want to find the min. And then you see in the lower left-hand corner, left bound. That means you need to be on the left side before it hits the minimum and push enter. Then it says right bound. Use your arrow, go around to the right side and make sure that your minimum is in between your left and your right bound. Then hit enter again. And this first point, and I'm going to tell you, I must have copied this from the book because I only have 3 decimals. So that's our first horizontal tangent. This is the minimum here. Now I'm going to do the same thing, only now I'm going to look for the maximum, the highest point in that spot. And that will be that coordinate point. And we have one more. That's also going to be a minimum. So each time you're telling the calculator, second trace, calculate the minimum. This is calculating the max. And this is calculating the min to find each coordinate point. And those are the 3 that have horizontal tangents. Okay, so if we look at this, first of all, I want you to think about what is x times x equal? That's just x squared, right? So if we use the power rule, we bring the exponent down, subtract 1 from the exponent, and that's the derivative. If we look at the derivative of each one and multiply it, that would be 1 times 1, which is 1. Notice these are not the same. There is no rule that says I can just multiply the derivatives. See back here? This rule, there is a sum and difference rule that we just take the derivative of each one and then add or subtract according to the equation. The product rule isn't quite so nice, but it's not awful. Now, I like this notation better. U v prime plus v u prime. So basically, we're going to take each part of the product times the derivative of the other part and add them together. And to me, it makes sense when we are doing product rule that we are using addition for the product rule. We look at a lot of different things, like when you multiply bases, you add the exponents. Add and multiply kind of work as a team. So let's look at this. When we're talking about this UV are functions, all right? So like this is one function times another function. I'm going to call x squared plus 1u times v, which is x to the third plus 3. So to find the derivative, I'm going to take u, x squared plus 1, times v prime, the derivative of v, plus v x to the third plus 3 times u prime 2x. So notice this is u v prime plus v u prime. Now I'm going to simplify. Just distribute backwards. 3x squared times x squared is 3x to the fourth plus 3x squared. Bring down the plus. Now distribute the 2x. 2x to the fourth plus 6x. Now I'm just going to combine like terms. For my final answer. So my derivative function for f is 5x to the fourth plus 3x squared plus 6x. All right, so just like your product rule uses plus, your quotient rule uses minus. Now, what I always do, whatever is on the bottom, I start with the bottom, square the bottom first. Then whatever on the bottom is what we start with on the top. With product rule, it's not quite so important because we add. But with the quotient rule, because we're subtracting, order is very important. So whatever on the bottom is what we start with on the top. Then we take it times the derivative of the top minus the top times the derivative of the bottom. Okay, so this says differentiate. That's the verb to find the derivative. So f turns into f prime. Remember what I said up here. You start by whatever on the bottom and you square it. Square the bottom, then whatever on the bottom is what you start with on the top times, now let's think about this. U is on the top, V is on the bottom. So I'm taking the bottom times the derivative of the top minus the top times the derivative of the bottom. The hardest part of the quotient rule is simplifying it correctly. So the first thing we're going to do is distribute the 2x back. 2x to the third plus 2x. Here's where people make careless mistakes. We have to distribute the 2x back and we have to subtract. So if we distribute this, 2x times x squared is 2x to the third minus 2x. Now I need to distribute the negative all the way through. So then we have minus 2x to the third plus 2x all over my denominator. Now I can combine like terms. So my 2x to the thirds end up canceling. So I have 4x over x squared plus 1 squared. So the derivative for this function is 4x over the quantity x squared plus 1 squared. So sometimes they just tell us the numerical values of each of the functions. You must be very careful though. U and V are not numbers. They are functions, U and V. So we start with the generic product, UV. We are looking for the derivative of y. Since U and V are being multiplied, I'm going to use the product rule. U, V prime plus v u prime. Then I can find the numerical value at 2. One thing that I sometimes do, I'm going to rewrite each of these. U is 3, u prime equals negative 4, v equals 1, v prime equals 2. So I'm just going to kind of focus on these numbers here. So u is 3 times v prime 2 plus v 1 times u prime negative 4. Then we're going to multiply. 3 times 2 is 6. 1 times negative 4 minus 4 equals 2. So what I want to just caution you on, when you see this, pay attention to the fact they are functions. So because two functions are being multiplied, you have to use the product rule. All right. The power rule for negative integer powers basically just means it's the same rule. For example, if I have y equals 3x to the negative 2, whatever the exponent is, you multiply times negative 6, and you subtract 1 from the exponent. So be careful, if this is negative, you need to subtract here. All right. So with example 7, to find an equation for the tangent line, we need two things. The point they give us, and we also need the slope. So what I need to do to find the slope of the tangent line is the derivative of y. Now, what I can do, if I have an equation that my denominator is one term, I can separate this and make two separate functions, two separate fractions. Okay? It's just going backwards from getting a common denominator to giving each their own denominator. Now, if we have x squared over 2x, that simplifies to x over 2. Plus, now I want to move this x out of the denominator. Our goal is to rewrite everything using exponents. So that would be 3 halves. Now I'm only moving the x, so everything else stays the same. If the x is positive in the denominator, when it moves up, it becomes negative in the numerator. And we also have, you can rewrite x over 2 as 1/2 x, and maybe it would make more sense to do it this way. So now I'm ready to take the derivative. So the derivative of 1/2 x is just 1/2. Then I'm going to bring my exponent down, multiply times 3 halves, so that becomes negative 3 halves. X to the negative 1 minus 1 is negative 2. And then I'm going to rewrite, moving my x back to the denominator because it's easier to evaluate with a positive exponent. I manipulated algebraically up here so it's easier to take the derivative, but as soon as I'm done with the derivative, I'm going to move it back to the denominator so all my exponents are positive. Okay, if this is my derivative equation, I find my slope by plugging my x value in for x. 1/2 minus 3 times 3 over 2 times 1 squared Well, that's just 3 over 2. 1/2 minus 3/2, negative 2/2, which is negative 1. I have my point. I have my slope. I can now write the equation. Y minus my y value equals my slope times x minus my x value. Okay, this is actually pretty straightforward. Second and higher order derivatives. If we start with the first derivative, we take the derivative of the derivative to get the second derivative. Then I take the derivative of the second derivative to find the third derivative. So notice if there's 2 hash marks, that's the second derivative. If I have 3 hash marks, that's the third derivative. So the actual process is much easier just by actually doing the problem. This says find the first 4 derivatives. So this starts with y. So my first derivative gets a 1 hash mark. The derivative of x to the third, 3x squared. The derivative of negative 5x squared minus 10x. The derivative of all constants is 0. Now I take the derivative of the derivative, which is the second derivative. The derivative of 3x squared, bring the exponent times 3, 6x to the first, minus 10. So remember, everything's 1 degree less as we go down. Now I do the third derivative. The derivative of 6x is 6. The derivative of my constant is 0. I'm looking for 4, so I need 1 more. And the derivative of a constant is 0. So each time we're just taking the derivative, again, of both sides. And we won't do that last example